Imagine unlocking the secrets of X-rays, CTs, and more with a single groundbreaking principle, even if you're an absolute beginner. I'm Alec Palmerton, and as someone who scored in the top 0.1% on Step 1 and matched into Harvard MGH, I've learned the importance of mastering the fundamentals. In this video, I'll reveal the simple yet revolutionary insight I gained from a Stanford professor whose brother won the Nobel Prize in Physics, a secret most radiologists don't even know. Let's jump in. My experience at Stanford may be a lot like yours. I was learning about radiology and X-rays, and I just felt overwhelmed. I was sitting there and I was Googling things like X-rays for idiots or alternative careers for people who fail out of medical school. Because honestly, I kept thinking, wow, like what's wrong with me? How does everyone else seem to know this, and why can I not understand this? In retrospect, I think that the problem was that the professors were speeding through the slides just filled with jargon. They'd say things like consolidation or infiltrate or speculated mass. They acted as if we knew what they were talking about without really having taught us fundamentals, and they weren't really giving many, if any, explanations of the underlying concepts. Then, in a moment, everything changed. I remembered a conversation with Dr. Gildshoe. He's a renowned Stanford professor whose younger brother won the Nobel Prize in Physics in 1997 for research in cooling and trapping atoms using laser light. He confirmed this one principle that changed how I looked at radiology forever, and in turn helped me see the power of mastering principles so that I didn't have to be buried under thousands and thousands of details. The principle that he shared was really simple. It's that X-rays pass through different tissues to varying degrees. If they pass through, what you'll see is it's darker on the X-ray itself. So lungs are dark because there's nothing there to block the X-rays getting through. They just make it through to the film on the other side. If they don't pass through, they're lighter. So that would be like bone. Bone is very dense, and so the X-rays that come in bounce off of it and they're not detected by the detector on the other side. So what this means on a fundamental level is that what determines whether something is bright or dark on an X-ray or a CT is whether it passes through. And whether something passes through or not really comes down to nuclear density. If this sounds really scary to you, it really isn't. It really just means that on a periodic table of the elements, like the one that you see in high school, chemistry classes, it really just means it's lower on the periodic table, because everything that's lower on the periodic table has a higher nuclear density. And if there's a higher nuclear density, then X-rays won't pass through. This is incredibly powerful. What you're able to do then is basically predict and explain why certain tissues appear darker and why certain tissues appear lighter. It also explains things like contrast, and when you use contrast and when you wouldn't, what sorts of stones would appear radiodense and what stones would appear not radiodense, as well as a host of other things. Let's take a simple example. So something's organic, like in organic chemistry, it just means that it's based on carbon. And so it has elements like carbon and hydrogen and nitrogen. Those elements are very high on the periodic table. They're not very then nuclear dense. And because they don't have a lot of nuclear density, the X-rays are going to pass through. And when they pass through, they're going to be detected by the detector, which means that they're going to appear darker. Inorganic elements, so things that are basically farther away from carbon on the periodic table, they're going to have a higher nuclear density. So those would be things like calcium or phosphorus or iron. Those are things that, because of their higher nuclear density, are going to cause the X-rays to bounce off of them and then not be detected on the other side. If they're not detected on the other side, they would appear lighter. Do you love learning principles rather than memorizing details? Consider hitting the like and subscribe buttons so you can master, not memorize, for higher scores faster. So as we said, what elements are more versus less dense? So elements that have a greater nuclear density are going to be lower on the periodic table. In other words, they're going to have a higher atomic number. Let's think about soft tissue. So one of the things that was really confusing to me when I was learning radiology is that they would put up a slide that said something like lungs are going to be black and fatty tissue is going to be sort of darker, and then denser tissue is going to be lighter and bone is going to be white. But they didn't really explain what the principle was behind it, and so I was just memorizing it, and it was something that I had a hard time remembering and using because it was just something that I was regurgitating. But let's think about applying this principle to, say, soft tissues. So how would soft tissue appear on X-rays or CTs? Well, let's go to our periodic table. So soft tissue is basically composed of organic elements. So things like oxygen or hydrogen or carbon, they're going to be darker because they're going to be less dense. Because they're less dense, the X-rays are not going to bounce off them, and so they're going to be detected and therefore going to be darker. Let's think instead about bone. So how would bone look on X-ray or CT? So bone is really white. The reason is that it's got things like calcium in it or phosphorus. Because those elements are lower on the periodic table, they are going to have a higher nuclear number, higher nuclear density, and therefore fewer of the X-rays are going to be passing through them and fewer of them are going to be detected on the other side. So they're going to look very white. Let's think about blood. So how would blood appear on X-ray or CT? It generally is going to be lighter. Why? Because it's going to have, in addition to the normal organic elements of carbon and nitrogen and oxygen and hydrogen, it's also going to have iron. And iron has a higher nuclear number, therefore a higher nuclear density will not allow the X-rays to pass through nearly as well, and so it's going to appear lighter because fewer of the X-rays are going to be detected by the detector. So another thing that comes up is the use of contrast. So contrast is something that either you swallow, that you ingest, or that you give intravenously, and it can be used to better visualize various structures. Now, what do you think, if I'm trying to visualize various structures, what are the most common elements in CT or X-ray contrast? Let's think about that. Well, they end up being things like barium or iodine, which again, if we look at the periodic table, are very, very far down the list, which makes sense because they would have a really high nuclear density and thus not allow the X-rays to penetrate. And so they would appear very bright on the X-rays or CTs. Let's think about IV contrast. So what's the purpose of using IV contrast? So IV contrast distributes to tissues via the arteries and the capillaries. And again, because it has elements with high nuclear density, it's going to basically light them up. The reason being is that because they're denser elements, they're going to not allow for the X-rays to penetrate through them and therefore look brighter. Let's take another example. Let's look at two images. One thing that I struggled a lot when I was an intern or when I was in residency was understanding like, okay, is this image contrast enhanced or is it not contrast enhanced? You can actually tell using this one principle of how X-rays and CTs work, you can tell very quickly if an image, if a CT image has been enhanced by contrast or not. So let's look at these two images. In the top versus the bottom, which is enhanced by contrast and which wasn't? You can tell that the bottom one has been enhanced by contrast, and the way that you can tell is because it's a lot brighter, right? Because the contrast, again, it carries elements that have a higher nuclear density, the X-rays are gonna be bouncing off of them, not reaching the detector and therefore looking brighter. Let's think about when you would even use contrast. You can actually explain this using the same underlying basis, which I actually find to be an easier question to ask, since under most circumstances you want to use contrast if you can, right? If there's not a contraindication, if they don't have kidney failure or something like that, for the most part, you want to use contrast. And so it's more useful to think of the situations in which you don't want to use contrast, because those are a lot fewer. If you just memorize those, if you understand those, it makes it so that all of the other ones are pretty much the cases that you would want to use contrast. IV contrast, like we said, makes tissues brighter because it has a higher nuclear density. And so you shouldn't use IV contrast if the thing that you're looking for is already electron dense. So let's think about it. So you don't want to use contrast if you're looking for, say, a fracture, because bones themselves have a high nuclear density. You don't want the contrast to interfere, because if they're already bright, you don't want to make the rest of your picture brighter, which is going to make it harder to see the fracture. Probably the classic one is an intracranial bleed. If you have a stroke, one of the first things that you need to do is to rule out a hemorrhagic stroke, because if you're going to give a thrombolytic, you don't want to make that bleeding worse. And so you need to make sure that they're not bleeding. So you do a CT non-con of the head so that you don't have a bunch of contrast that's then going to show all the bleeding in the brain. Since the bleeding, the blood, because it has iron in it, is going to already be brighter. And so you don't want to make it harder to see that blood. Another case that you generally don't want to use contrast are for kidney stones. Again, a lot of the kidney stones, most of the kidney stones have a denser element in it. So for example, calcium stones have calcium in it. The struvite stones that you get in, say, a urease positive bug, those have magnesium and phosphate in it. And so those are both denser elements. And so you don't want to enhance those images with contrast, because you're basically going to make it harder to see the things that are already going to be bright, right? If you don't give contrast, everything is going to be dark except for the thing that you're looking for. Whereas if you're giving that contrast, it's going to make it harder to see the things that you're already looking for. Let's think about something like a CT angiogram. So a CT angiogram, so angio is vessel, graphy means study. It's basically where you're injecting contrast into a vessel and then doing a CT of it to visualize that vessel. And so how is that different from a normal CT with IV contrast? Basically, in both cases, you're giving IV contrast. The difference is that in a CT angiography, you're timing the CT so that most of the IV contrast is in the arteries, right? They've worked out how long it takes. If I inject a bunch of contrast in your veins, they know roughly how long it takes to get to your heart, and from your heart, roughly how long it takes to get to a variety of arteries. And so they wait until the contrast should be in your arteries, and then they do a CT of it so that they can visualize the arteries before it's already distributed to the capillaries. As opposed to a CT with contrast, just a CT that's enhanced with contrast, you're basically giving the contrast in the veins and then waiting longer for it to distribute to the capillaries so that you can see the tissue itself as opposed to focus on the arteries themselves. In a patient, this is what it might look like, right? So this is an example of a CT angiogram, and the way that they're doing it again is you can see these arrows, and you can see in the arrows that the vessel itself is very, it's like white, basically. And the reason is that you've got all of that contrast that's sitting in that vessel, and it is blocking the x-rays from going through, and so you're able to see the vessel itself very clearly. If you found value in learning how fundamental principles can accelerate your mastery of radiology and any other subject for the USMLEs, subscribe now for more videos that will help you understand key concepts and reduce memorization for higher scores. Also, click the link on the screen to watch the next video and take your skills to the next level. Thanks, and I'll see you in the next one.